Hello, welcome to section 4. We're looking at exponential functions. Our first goal is to answer the question, what is an exponential function? They're brand new in intermediate algebra. Our second discovery will be the fact that a constant growth rate is all you need for exponential growth. If the growth rate stays the same, you've got exponential growth. And the third big goal in our first introduction to exponential functions is to see that whenever you've got exponential growth, you have a constant doubling time. So we're going to use the formula for accumulated interest. I say accumulated interest to explain that A in the formula. And notice how there's an exponent nt, and t is often our variable. We want to know what happens as time passes. And that variable is in the exponent. This is an example of an exponential function. Now, similarly, the formula for continuously compounded interest also has a t in the exponent. That e is a constant like pi, the r is the rate, the p is the starting value. But the point here is that the t in the exponent is a variable. That's how we can spot an exponential equation just by looking. So let's look at this first example. This is the graph of the amount of money in an account that earns interest at a constant rate of 15% per year. I'm going to emphasize that constant growth rate here. This is growing at a constant rate of 15% per year. And when you look at that curve, it doesn't look very constant. That's an exponential curve. So we started with $150 and it grew at 15% per year. Now, one of the big ideas I want you to get out of this is that the doubling time is constant. If you have a constant growth rate, then you have exponential growth, and the doubling time is constant. So the time that it took the account to go from $150 to $300 is the same amount of time as it took to go from $300 to $600, from $600 to $1,200, and from $1,200 to $2,400. That doubling time is constant. And I'm going to introduce the formula at this point because it's fine to say that the doubling time is constant, but it's nice to have a formula for that. And here it is. Not too long from now, we're going to derive this formula. We're going to actually use other equations to make it. Now, there's a lot going on in this formula that's new. For example, it's a time, but it's a doubling time. So notice how the subscript is the word double. You could use a capital T or something like that. This is the time that it takes something growing at a constant rate to double. Now, the numerator there is the natural log of 2, and that's a function. That's a new function to us. The natural logarithms on your calculator. So this is the natural logarithm of 2. That's because we're doubling. If we took the natural log of 3, that would tell us the amount of time that it took for the amount to triple. Now, if you check out in your calculator, the natural log of 2 is approximately 0.69. So we can approximate this rule with a little bit of a shortcut, and that is 0.69 divided by the rate. Bankers use what's called the rule of 72, and that's, of course, an approximation for 69. So a reminder in this first sentence, for that reason, regardless of the starting amount P or the rate of growth R, all quantities that grow at a constant growth rate also have a constant doubling time. And because that's true, the doubling function, y equals 2 to the x, is an excellent place to look to understand exponential growth. So we're going to look at this curve, and later on, if you skip ahead to sections 9 and 10, you're going to see that we graph using exactly this same setup. We use the fact that a constant growth rate means that we have a constant doubling time to graph all sorts of exponential equations. So this will pay off in the long run. So we're going to make a table. Now, we'll quickly learn that our table isn't terribly useful, but it's a nice start. It's exactly what you'd expect to start with. So we're going to plug in some values for x. I just chose some positive numbers from 0 to 5, some integers. and I put that into our formula. I made those the exponents on our formula there. So when we plug in x equals 0, notice that we have the expression 2 to the 0th power, and that's equal to 1. So our first output at x equals 0 is y equals 1. So we can graph that point, and that's the first point that we've found. When x equals 1, we see that 2 to the first power is 2. So we've got our second point at x equals 1, y equals 2. And we continue in this way. And you see that these are disappearing off of our graph. So here's a table. It's given us some information. Maybe the graph is more useful. Take a look at that and notice that it has an asymptote. In other words, it's getting closer and closer to the x-axis without ever touching it. And we'll talk about that when we talk a little bit more in the next example about the halving function. So here's the halving function. As we go to the right, we take half as much as we had before. So if we start at 1, of course, when x equals 0, y equals 1. That's true for any base other than 0. And we've got a base of 1/2. So we go to the right and we take half of that. That's half as much. We go to the right again. We take 1/4 as much. We go to the right again. We take 1/8 as much. Each time we go to the right, we are half of the height that we were before. Now we are definitely getting close to the x-axis. We're definitely getting close to 0, but we're never going to get there. We're only going to get half the remaining distance as we go each succeeding integer to the right. Now this is a perfect time to talk about how the base affects the exponential. Notice that all of these are exponentials. There's a variable in the exponent. So the top one there, y equals 3 to the x power, clearly growing faster than the other two to the right of 0. But I do want to point out something. This same curve is actually the one below the others to the left of 0. It's actually down here below the others. So that 3 to the x grows the fastest to the right, and it falls the fastest to the left. 2 to the x is our doubling function, so that's the one right here in the middle, and it's in the middle on the left side as well. Notice that 1.5 to the x is actually the lowest on the right of 0, and it's the highest on the left of 0. So over here, it's actually the top one up there. So let's solve some exponential equations. Now we don't have any powerful hardware to do this yet, so we're going to do this in a very arithmetic way. So the examples that I'm giving you at this point, this won't stay true much longer, but at this point the examples we're looking at are fairly contrived. It doesn't take long for you to convince yourself that 6 to the x and that 36 on the right side both have the same base. So for example, notice that we can write the right side, 36, as 6 squared. So we're basically asking the question, what exponent on 6 is equal to 2? And so we can quickly convince ourselves that that's true when x equals 2. And going back and thinking about this arithmetically, when we plug that x equals 2 into the exponent there, we get 6 squared, which is in fact 36. So these are kind of silly questions. They are chosen because the bases can be rewritten as the same quantity. So if I take this next example, notice that 8 and 4 are both powers of 2. You could make factor trees to convince yourself of that. That 8, notice, has become a 2 to the 3rd power. So all we did there is a little substitution when we factored. Now on the left side, I'm going to show this kind of slowly. Notice that I've got parentheses containing what used to be the 8. But when one base has 2 exponents, we can simply multiply the exponents together. When one base has two exponents, here the base is 2, the two exponents are 3 and x, we can simply multiply those together. So that's exactly what we're going to do in the next step. So there's 3 times x as the exponent on the left. Now the bases are the same, so we can equate the exponents. We're basically just saying that the only way that we can get the same output is if we have the same input. And that's true because these functions are one-to-one. In other words, there's really only one way you can get one output. The function is, the exponential is a function, and so is its inverse, to use the vocabulary of the previous section. So we equate the exponents, 3x equals 2, and then, no great surprise, we divide both sides by 3, and there is our answer, x to the 2/3. Now, I will point out that if you take x equals 2/3 and you raise 8 to the 2/3 power, you'll be taking the cube root of 8, which will give you 2, and then you'll square 2, which gives you 4. Okay, 2 more like this, and again, you can quickly convince yourself that we're doing this, that we're able to do this at this point before we've got anything more powerful, simply because 9 and 27 are made out of 3s. So that's the first thing we're going to do, is see what we've got in terms of 3s. 9 became 3 squared, and 27 became 3 cubed. So we rewrote both of those bases with 3 as a base. Now, each time we have a base with several exponents, we can simply multiply the exponents together. So we're going to do that right now. I've shown this as a 2-step process. In the first step, I wrote the 2 times the 2x minus 8, and I also showed on the other exponent the 3 times the x minus 4. And then, of course, the distribution happened in the next step. We've got the same bases, so we can equate the exponents. So there's the exponent on the left equal to the exponent on the right. Let's subtract 3x from both sides and see what we get. When we subtract 3x from both sides, the 4x becomes an x. Now the variable looks like it's ending up on the left side, so let's add 16 to both sides, and we get 4. And you can check that out. It works perfectly. Your calculator is a perfect tool for doing that. Take a look at the right side here. Now, I see 5s, definitely. 5 squared is 25, but on the right side, I'm going to go through this a little bit more slowly so you can see exactly how this came to be. First off, I can raise 1 to the xth power, so I put parentheses around the 1/5 on the right side. On the left side, I did exactly what we've been doing. I rewrote 25 as 5 squared. Now, the reason that we are trying to get the fraction by itself on the right is because we want to know what the exponent has to have been. And notice that if you move the denominator into the numerator, that's the same as having a negative exponent. So notice I've given that 5 an exponent of -1. And now we're in the situation that we were in just a few examples ago. We've got the same bases. We've got one base with several exponents. We're going to multiply those exponents together, and that will give us, let's just clean it up a little bit, that will give us an exponent of 2x plus 4 on the left side when we distribute, and the opposite of x on the right. The bases are the same, so we equate the exponents. That gives us 2x plus 4 equals the opposite of x. Looks like we should add x to both sides. When we add x to both sides, we get 3x plus 4 equals 0. Of course, x plus negative x is 0 on the right side. Let's subtract 4 from both sides and then divide through by 3. So x equals -4/3, something else you can check out on your calculator.